All right, everybody, Soap Lab tomorrow. We will be making soap. Now, soap is made usually with fats or oils. Now, understand a fat and an oil are really the same thing. So, if it's coming from a plant source, plant or animal source, you can have solid fats. Okay, solid fats are typically from animal sources like um, tallow from beef or lard from pigs. Or you can have some solid vegetable oils like coconut oil, which is what we'll be using. Or you can have liquid such as corn oil, olive oil, or canola oil. Those are your typical cooking oils. Now, when we talk about these oils or what are called fatty acids, what we're looking at is the reason we call them fatty acids, or we can call them triglycerides, just something as you get older you'll have to listen to your doctor talk about. The fatty acids are this portion right here. So we have these branches. This is why we call it a triglyceride, because there are three branches on a glycerin backbone. So this is the backbone that holds these together. So we have glycerol that gets separated out in this process, and this is a byproduct. It's something that we'll just end up washing down the drain. And we have what is called a sodium salt. Now this is a salt that is soap. So this part is soap. Now we're going to talk more about the structure of that here in a little bit and why this is soap and what it does and why it's important. Now, tomorrow you're going to be using sodium hydroxide. Sodium hydroxide is, in the concentrations that you're using, is dangerous. If it gets in your eyes, it will cause permanent damage. Okay, so goggles are an absolute must. We're also heating it to boiling. So that's what this delta symbol here means. Actually, in this case, it means we're heating. The sodium hydroxide you're using will cause chemical burns. So if you get some on you, wash your hands immediately or wash that area immediately, then let me know. Wash first before you tell me though, please. I want to make sure that gets off of you as quickly as possible. Now, looking at soap. When we talk about soap as a molecule, you noticed it had sodium and then all of this. So it's a very, very long molecule. So there's 16 of these in there. I'm not going to draw all those. That would be ridiculous. So a quicker way to do this would be to draw it this way. Where every time we change directions, there's a carbon. So there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I drew too many. And so here we have a very shorthand version for the Lewis structure of soap. Now what ends up happening is that this is actually ionic. So this end, you have a sodium ion and an oxygen. So what ends up happening is you really get two separate things. So when you put this in water, or with water, you now get an ion. So here, water will attach to that, creating an ion dipole, but water will also do the same thing on this end. So this end of the molecule is very polar. Now, for us, that means that it's soluble in water. This end is nonpolar. Now, the reason that this is important is that soap is used to remove things that are not normally soluble in water. How that works is by creating a micelle. Now, the micelle is actually broken into two ends. When we call it polar, what we can say is that it's hydrophilic, meaning water-loving. So hydrophilic is the same as saying it's the polar end. Hydrophobic then would be the non-polar side. Now, what ends up happening is if you have something that is non-polar, like a fat from gravy or some other thing, that will be surrounded by the part that is non-polar, because non-polar objects attract non-polar things. So like dissolves like. So what ends up happening is your soap will attack whatever that is, whether what kind of fat is on your hands or whatever kind of dirt is there. If it's grease, it's non-polar. Water won't wash it away. Water won't dissolve it. So the soap will come in and surround it. When it does that, it creates a micelle with all the non-polar sides facing inward and the polar sides facing outward. And so now the outside of this micelle is polar and soluble in water. So then it can be lifted away and carried away with your water when you're washing your hands or whatever else you're washing. All detergents, soaps, work the same way, whether it's dishwashing detergent, whether it's clothing detergent, or whether it's soap, hand soap, it works the same way. It works by creating this micelle around the particle that is non-polar, not soluble in water, and it forms a soluble barrier around it for the water to pick it up and carry it away. Now, as far as procedure goes, when we're looking at procedure, this is a relatively simple process, but there are a couple things we want to point out. Okay, we're going to start with melted coconut oil, and that melted coconut oil will be at the center table. Okay, it'll be pre-melted, so it'll be heated and melted for you. So it'll be a liquid, so just use the provided graduated cylinders to get 20 milliliters of that. You're going to put that directly into your beaker that's already provided to you. There at the center table will also be an ethanol sodium hydroxide mix. This mixture, you need to make sure that if you spill any, please clean it up with a paper towel, because if that gets on your hands, it will sting and you're going to need to wash that off immediately. So you're going to get 50 milliliters. Again, graduated cylinders will be provided to you. Please make sure you do not swap these two sets of graduated cylinders. Leave them where they need to be. Now, you will need to stir this. This is one of the few times we'll actually use a glass rod. That'll be provided to you at your lab station. Again, we need to make sure we're over medium heat. Because we have ethanol in this, ethanol is very flammable. And so we do have an open flame. So you will need to be very careful with that. We want to make sure that we're using medium flame. So make sure there's about 3-finger width between the hottest part of the flame, the tip of the flame, and the bottom of your gauze pad. Now, very important to make sure you pay attention to number 4 in the procedure. If this foams up too much, it's going to go over the side and everything will catch on fire. Now that creates a hazard, and we'll talk about how to deal with that if it should happen to you at your station. This is where I say don't catch your lab station on fire, because this is where it will happen. If you need to remove your flame because you're getting a lot of foaming or you're getting a lot of bumping, which I'll explain to you in class, just simply take your Bunsen burner and move it to the side. Move it away from the beaker. Move it a far enough distance that the flame is not going to catch the ethanol on fire above it. Just simply grab the bottom, it won't burn you, and move it out of the way quickly. Now, you'll end up heating this until All of the ethanol is gone. Now do not smell it, okay? Don't stick your nose over the top of it, that's a problem. Typically what will happen is the foaming will subside. It'll stop foaming up. Once that happens is usually is when the ethanol is gone. Now, once you've done that, make sure that you turn your Bunsen burner off before you move anything. You're going to want to let this cool a little bit before you move it. Make sure you use a beaker tongs, put it down on the lab station, and let it cool down a little bit. There will be saturated sodium chloride provided to you. Then you will add that to your solution. Once you've done that, then the soap should coagulate after a time when it's cooled down. It should coagulate and rise to the surface. Once you do that, use a plastic fork that's provided. Please don't throw them away when you're done. Use a plastic fork. You can just scrape the soap right off the top. We're not going to be filtering this. Just place it on a paper towel. That'll absorb all the excess liquid, and then you're ready to start the testing process. Now, the testing process, you're going to want to start with 3 Erlenmeyer flasks. Those will be out and provided. Make sure they are clean because you don't want anything to taint your results. Most of your observations are recording the height of the suds and how long it takes for them to deflate or drop back down to where the suds are gone. The other test that you're going to have is with the pH. And so I will demonstrate the pH test and the setup for all the testing side when you are in class. This does not take very long, but it does require observations. All right, this is a fun lab, but you do need to stay focused. There is plenty of potential for danger on this, but please stay focused. Leave your cell phones at your seats. You do not need those for this lab. You can count to 20 or 30 seconds. It's not that big a deal. Please make sure that you come in with closed-toed shoes and preferably not wearing shorts. It would be better to have your legs covered for this, as any spills would cause some serious burns on this. So, otherwise lab aprons will be provided. All right, other than that, looking forward to working with you in lab.